So everything in space is moving, but there are different kinds of motion. So part of it is called the peculiar velocity, those related to the object traveling through space, and a recessional velocity, a result of the universe expanding. So here's the picture over there to the right. We have an observer. We have a galaxy cluster, and the galaxy cluster is moving around the center of mass and moving, rotating, orbiting, and moving towards the middle. That kind of measurement we can't measure very well. Anything that's close to us like that we can't. But when we're looking at a galaxy way, way, way off into space that is just moving because of the expansion of the universe, that we can measure, and that's what we're looking for to figure out this Hubble constant, or how fast things are moving away. So, limitations to Hubble's law. A common misconception is that all galaxies have positive recessional velocities. So positive meaning that everything is moving away from us. But there are a few galaxies that are actually moving towards us, and the biggest one is Andromeda, as we've talked about before. So its shift of its spectra isn't a red shift, it's a blue shift. So here is a local group of galaxies. There's a center of mass, and they're all kind of moving towards it, but they also have random motion as well. So those are the kinds of things we are not going to look at while we're trying to calculate this Hubble constant. So the search for the true Hubble constant. What is the rate that it's expanding? So think back a few slides to the slide where Edwin Hubble put on the bottom line on his graph the distance, and on the left-hand side he put the velocity, and then he made the line and he charted things across. If you take the slope of that line, the slope is the rate that it's expanding. That's the number we're trying to look at. That's what we want to know. How fast is this universe expanding? So there have been different studies, lots of groups of scientists that have tried to calculate this and to pin it down to a particular precise number. Why do we want to do that? We want to do that because if we wind the clock backwards, then we know how old the universe is from the time it began at what we call the Big Bang. So this was the Hubble study. They completed an 8-year effort to measure the expanding universe. These results were released in 1999. The team measured the Hubble constant, which is the slope of that line, at 70 kilometers per second per megaparsec, with an uncertainty of 10%. This means that the galaxy appears to be moving at 160,000 miles per hour faster for every 3.3 light years away from Earth, which is simply saying things that are farther away are receding away from us faster than the things that are closer. And that's the rate that they came up with. Here's their data chart. Pretty nice. They have a lot of data that is pretty much on that line. So the slope is the constant. Here we have the velocity on the one side, we have the distance on the other. You calculate the rise over run and get the velocity, or excuse me, the slope, then we end up with the Hubble constant. So it's just measuring how fast things are spreading apart from each other. So if you look at the middle ant on the top ruler there, and then you pretend this is an elastic ruler and you stretch it out, then the ant that's farthest away will actually have moved away farther in the same amount of time than the ones that are closer. And that's how the galaxies act as well. So knowing the expansion rate and calculating it backwards gives us the age of the universe. And that's what's referred to as the Big Bang, which we will talk about in future lessons. And it's not that Big Bang theory. Oh, thank goodness. So let's look at kind of a map. So we have the Big Bang, where we think everything started as a singularity, and you can picture that as sort of like a black hole. The black holes are a singularity where all this energy or this mass is compressed into a tiny spot. Something released it, and it was energy. The energy causes huge expansion. The energy converted into matter, which is, according to Einstein's theory, E equals mc squared. We have energy on one side of the equation, we have mass on the other, so they are somewhat interchangeable. So at the beginning, it was small, we had an expansion, things are spreading apart from each other farther and farther. The galaxies get larger and larger as they combine with each other, and there's man clear at the edge there. And we don't know exactly how long it is, but by knowing that expansion rate and winding it backwards, we kind of come up with the spot at the beginning. So how old is the universe? So you get a couple equations going here. The distance of something is equal rate times time. You've known that since grade school. You can rearrange a little bit and have time equals distance divided by the rate or the velocity. But Hubble's law, from what Hubble came up with, is velocity is equal to the Hubble constant that we're trying to calculate by observation and mapping times the distance. So if we combine those together, we substitute in for velocity and we put into that hd where the v is in the top equation, the d's cancel. Now we get the age of the universe as just simply being the bottom equation there, t, the age, the time of the age, equals 1 over the Hubble constant. Just that simple. We have to do some conversions to make it make sense, but t equals 1 over h. So the age of the universe is dependent all on what the Hubble constant is. Now there's some assumptions here. We would have to assume that the rate of the expansion of the universe was constant since the beginning of time. We don't know that that's true. It could have expanded at a faster rate, which they call inflation at the beginning. It could have been constant. It could have been slower and then gotten faster. We don't really know. So the best we can do is estimate. Excuse me. So look at this chart here. This chart is showing different studies that were done to find this expansion rate. So the Hubble study in 1999 said, well, the Hubble constant's about 70. The Spitzer in 2012 said it's about 74.3. Holy Cow, 71.9. The Planck, 67.4. Hubble Shoes, 74.2. The very latest one that has just come out is 70. So they're all kind of in the same ballpark, but they do make a difference when you start putting them into the calculator and the equations, how old the universe is. So for your homework today, for this assignment, you will be taking the data, it will be on your worksheet, the same data, and you will be calculating how old the universe is by those numbers to see the difference, how much difference it makes. So email me if you have any problems or questions. Always happy to help you. See you later, Gators. Bye.